shining. Left side, right side, how to pa pa pa. You are king.
That's why I gotta kill him every time. Gotta watch him bleed too. Don't ever say it's over if I'm breathing. Racing to the moonlight and I'm speeding. I'm headed to the stars, ready to go far. I'm star walking. You wrap around me and you give me love, and that's why night after night I'll be loving you right. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, week. Monday, Tuesday, Wednesday, Thursday, Friday, 7 days a week. Every hour, every minute, every second for life. The darkness no longer scares me. I'm chasing and hunting, and this time I'm coming for life. Be the last one to laugh when you run out of breath catching life. I'm not materialistic, but I got a thing for you. Treat the world like a time pulling strings for you. Just to save you, I give all of me. I can hear you screaming out, come
Dun 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 dun.
Dun, 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 dun.
Dun, 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 dun. Hey!
Hey!
Way too early for that, huh?
Yeah, no, that's okay, that's okay. But hi, Xander.
Hi, Jen. Hey, everybody. Today we're well, actually, you should probably be the one talking about what we're doing today.
Yeah, to you,
Yeah, put the glasses on. Yeah.
So today we're learning about quantum
magnetic leviosa.
levitation. Yeah.
Levitation?
Yeah.
Levitation.
Levitation.
Before we get into it, because we just started, I figured that we should maybe just chat for a little bit, introduce ourselves to some more people.
Yeah, absolutely.
Because you guys need to buckle in for the ride we're about to go in.
Yeah, apparently this is going to be something really crazy. I'm just here to like learn.
This is education.
Education.
We're learning.
Wow. When do you ever see VTubers do educational streams?
Like never.
Right?
Actually, that's a lie. That's a
lie.
lie.
It happens. Like
I feel like it does happen, but it happens in a way where it's more like you're passively learning rather than actively learning.
Yeah. It's like you're learning from context rather than actually having things explained to you, right?
Exactly.
Yeah.
It's like, have you ever seen, oh gosh, what's his name? There's this guy, who he's like a he's like in a white lab coat, and he just like does random ass experiments and like lets chat control robots that he makes and stuff.
Owo's lab, right? Owo's lab. Yeah. He's so good.
Yes. He's so funny.
Did you see the Freddy Fazbear? So he rigged his whole house so that chat can control cameras and close doors, and he dressed up as Freddy Fazbear. It was so cool. It was so cool. And they would be like exclamation point kitchen, exclamation point garage, and like they would be like, oh my god. It was so cool, sick. Dude. Yeah.
What? That's insane.
And like it was actually kind of scary because like when he picked up the camera, he would like just scream into it.
That is awesome. Yeah. Wait, that is kind of scary. I can see that being frightening.
Okay, wait, we should introduce ourselves. Hi guys, my name is Xander. I am a vampire VTuber e-boy singer dude. I'm shit. I forgot how to introduce myself. It's been so long. I've been playing as my character that I forgot how to introduce like me actually.
What's your character's name?
Hey guys, my name's Officer Tiny Wang.
That's it. That's a Tiny Wang. I knew you're a police officer. I forgot your name.
Yeah, I mean he's going through a whole arc, but that's not important. Jun, introduce yourself.
Hi everybody. My name is Junakane, your resident himbo pirate. And today we're learning about quantum magnetic levitation.
So what is quantum magnetic levitation? Yeah.
I was just about to actually ask you that. What do you think quantum magnetic levitation is?
Okay. So, I have no clue, but you know what? As a very educated man, I'm gonna make a very educated guess, and I'm gonna say it has something to do with magnets on either side of an object making the thing float.
No,
not even close.
Guess that.
Wait, did I actually?
No, you didn't.
Oh, what the heck, man? What are you giving clear? What do you? False
It does
hope,
have to do with
guys. I
magnets.
hate this guy.
It does have to do with magnets. It does have to do with magnets. No, don't worry. You're on the right track. You're on the right track.
Okay.
Yeah. So quantum magnetic levitation. Now Xander.
Yes.
The question for you is, do you know what quantum means?
The only time I've ever heard the word quantum is in like a Marvel Cinematic Universe movie.
Okay,
Probably the Ant-Man or something.
So the most easily way, like the easiest way. Hold on, I just realized that my mic might be.
Oh yeah.
messed
Yeah.
up.
Just work
No,
on
okay,
that.
we're good.
Also, chat, can I get a volume check
Okay.
just to make sure Jin and my volume?
check.
Yeah, volume check. Just tell me if Jin's level and my level and everything else is
your
all
mom.
good. Yeah, your dad. No, shut up. Shut up. You're talking about my family that we manage. You know, it's not cool. Oh my
Got
god.
him.
You're gonna make me
Got
break into my
him.
Officer Tiny Wang voice and I'm gonna complain and scream.
Officer Tiny Wing. Anyhow, so
Yeah.
So break the word apart. What does it sound like it would be about?
Break the word apart.
Just quantum.
Quantum. Q and
Think of other words that like
Okay.
sounds like quan.
You're gonna hate how my brain just worked,
Okay.
but the only word I saw in there was ant, so I took ant out, and then all I got was cum. Cum ant.
Whoa.
Or ant
Whoa.
cum. I don't. fucking
Oh my
know.
god. Oh my god.
Okay. What other words start with Q? U like quant.
Quan.
Dude.
Think of like quant something.
Quartz Minecraft.
No.
Oh
No.
god. Dude. Look. The farthest I've ever gotten in any field of science was physics
Okay.
12.
That's okay. So quantum broken down. It has it quant is in like quantity, like numbers. Yeah.
Okay.
So the idea of quantum is looking at the measured amount of energy of different things and looking at like the like quantity of energy proportional to the magnitude
I see.
that of the frequency that the energy is like moving at. So that's the idea behind quantum. And so quantum is used in a lot of different things because most of those things we're looking at the measurement of energy in comparison to the frequency of its of either its waves or different things like that. So usually we'll see quantum in relation mainly with electrons. Because they do a lot of funny, wacky shit. Because we'll talk about that more later. They're very funny guys. They're very funny
Electrons.
little guys.
It was like
Yeah,
there was
electrons.
like electrons, protons, and neutrons or something, right? Like those
Yeah,
I remember learning that in high school.
Yeah,
Okay.
that's good.
Okay.
That's good. Okay, we're on the right track.
Yeah.
Okay, so with that being said, quantum magnetic levitation. Let's go ahead and we can go ahead and see what it's about, right?
Okay. I'm ready. What is this?
So,
Tina.
this is
Bacchus.
physics.
Sorry, I'm just reading words.
This is physics. Yeah.
This is physics. Okay,
so-
I've never
yeah, this is
seen this in physics.
Yeah. So we've got the equation for magnetic fields. We have the equation to find the amount of energy in an electron. We've got a bunch of stuff about electric fields and stuff like that. But obviously, this looks like a bunch of mumbo jumbo. Who gives a shit about this? Fuck that. Let's go watch
screw
a
that.
YouTube video.
Oh, YouTube
Yeah,
video. Let's
screw
go.
that.
Okay,
Yeah,
I'm ready.
YouTube
I'm
video.
ready. I love videos. I love videos.
Quantum magnetic levitation. This is
Quantum
from a
magnetic
convention in
levitation.
2011.
Yeah.
And we're looking at superconductivity group. So if you look at this,
Locking.
this is quantum magnetic levitation in its rawest form.
Wherever I put it.
It's pretty cool, right?
See, this
You
is
see how it's like
quantum
just
Yeah,
a
yeah, yeah.
floating object?
It's just floating,
Now, what
yeah.
do you, now, science is all about observation and testing. So what do you observe here?
upside down,
Right.
and it
What
stays
do I
locked.
observe?
So the fact
So
that it's
it really
superconducting
seems
is
like.
locking the magnetic field in 3
Yeah.
dimensions.
Okay, wait.
right?
Does
Yeah,
the
exactly.
I'm assuming like there's some kind of nitrogen coming from this? Is like does that matter?
It can rotate
At all?
Yes. That's good observation. Good observation.
Okay,
so what
okay,
does
'cause that's-
nitrogen do?
because
So
it,
it stays there
well,
on the,
I don't.
the X
It's
and
I know
Y,
it's
but
like
not-
freezing.
but
It's like
it
it brings up the
pivots on
freezing temperature or
the
something
axis
of
of
an object,
okay,
right?
okay.
And that's why the smoke is coming out.
It will again
Kind of. Okay.
I'm
on the
gonna
axis of the
assume,
magnet, because
since you talked about
it makes
electrons earlier,
sure
it's probably some kind
that
of
the magnetic
chemical
field inside
relationship
of it
between the nitrogen and
stays
whatever
the same.
is on the.
Not necessarily.
No?
Chemistry and physics are very, very closely related.
Okay.
Because of the fact that, like you said, chemistry is just reactions based off of physics, right? So
Yeah.
let's say the whole idea behind the chemical table of elements, right?
Yeah.
So you've seen the table of elements before.
Yeah,
The
yeah.
idea behind a table of elements is that each number at the top of above those elements are related to the number of protons
different height
that
configuration.
that
It can even lock
element has.
way.
And so protons being really cool are also in physics, right? You know, we talk about protons,
Yeah, yeah.
electrons,
Yeah, yeah,
neutrons.
protons.
locking
Yeah.
it upside down.
Yeah, and so basically, if you were to, let's say, use physics, this is like the whole idea behind alchemy, right?
Yeah.
In alchemy, is it not gonna go past this? There we go. Okay, yeah. So hold on, I'll get back to this in a second.
Yeah.
Fuck, what is going on?
Oh no! Bright screen, flashbang. I'm sorry, guys.
Flashbang.
Okay.
Yeah. So alchemy, the whole like fake science of alchemy. The idea is they're trying to make like gold, right? They're trying to make shit like that.
Like transmute a material from something else to gold. or-
Exactly. They're trying to like the whole idea of it was trying to make gold, right? Which the idea behind that is that if you were able to split protons off of one element and shove it into another element, you can make gold, because the whole idea behind an object of like an element is the number of protons that are attached to it, right? So that's just explaining how close like chemistry and physics are related.
I thought
right,
protons were like always stagnant. Like that's a number that never changes it within like a chemical
Well,
formula.
that's why I was saying saying that alchemy is like a fake science, because they're trying to basically
I understand.
make
Yes.
it.
Okay. Yeah.
But if we want to look at chemistry, right, you can make different compounds by combining different elements together and things like that. So for example, we can make water by combining hydrogen to oxygen, and they're both bound by covalent bonds, which are
Valence electrons or something, right?
Valence electrons. You actually know. Let's
Yeah,
go.
I remember
That's
this. I
awesome.
remember
That's
this
awesome.
from high school.
Good. Okay. So let's move on to more. O2H will kill you, dude. No.
Wait, O2H. Wait, just real quick, just so I can refresh my memory.
Yeah. Yes.
What does the 2 represent again in the H2O? Does that represent the amount of hydrogen or electrons in the hydrogen? Or
No, that's the number of hydrogens that are connecting to the oxygen.
to the oxygen?
So,
Okay.
Yeah. So if you have two, it's H2O, which means you're having 2 hydrogen atoms connecting to 1 oxygen atom, and that's
That
what's
makes
creating
water.
water.
Got it.
Yeah.
Okay.
So yeah. Very cool stuff. So you want to know how to make things float, do you?
Yeah.
Nice. But using normal ways with fans, engines, or wind is too easy and too lame. And you want to be extremely difficult on yourself and others around you, right?
Yeah, I want to be impressive and flashy. That's what I want.
Yeah.
Yeah.
Well, I have good news for you.
Okay, I love good news.
Quantum magnetic levitation.
Leviosa. Oh, levitation.
Leviosa.
Leviosaur. Magnetic Leviosaur.
Magnetic Leviosa.
Magnetic
So,
Leviosaur. Yep.
let's talk about magnets, because obviously quantum magnetic levitation has the word magnets in it, right?
Yeah.
Xander, what do you know about magnets?
What I know about magnets is usually there's a north and a south pole. I don't know. That's
Okay.
like what you call it. But there's different poles.
Yeah, yeah.
One is with a plus and one is a negative. I don't know what those mean, but it
Okay.
determines whether it repels or attracts to like based on which, you know, whichever the other magnet is currently. Yeah.
Yeah, that's pretty good description of magnets.
Oh, thank you.
So, yeah, of course.
So you guys are smart.
As you know, magnets have what we call a magnetic field. And now let's go ahead and go into what this picture is showing. So you said that there's a north end and a south end, right?
Yeah.
So we see here on the magnet, there's north and south. And we say positive and negative based on the attraction or repulsion. But in reality, there's nothing that's positive or negative about this situation. What a magnetic field is we've got electrons going around this material. So let's say it's a metal that is magnetized, right?
Yeah.
And the direction on which the field is going, so for example the south end versus the north end, is actually looking at the direction of how the electrons are spinning. So let's say an electron is spinning, and obviously it's a 3D thing, not 2D thing, but I'll just say let's say one's spinning clockwise and one's spinning counterclockwise. That'll change the direction of the magnetic field, and that'll actually change how the
electrons move,
you know.
or?
Yeah, not necessarily how the electrons
okay.
move, but how like it is attracted or repelled against another field, right? So if you have two electrons that are spinning the same way same way as each other, and they run into a wave coming at them of electrons also spinning the same way, they'll repel because they don't want to be next to each other because they're looking to balance themselves and make
each other.
Yeah, they hate each other's energy.
Yeah, I don't like the other people. It would be like you know, like different different crews, you know, like a different South crew and another South crew. We can't be the same crew.
Exactly.
Yeah,
exactly.
we can't join together.
Crew.
We gotta be stay on our own turf. Okay.
Alrighty. Okay. So, you see those cool lines going off the magnet? Let's look. See the cool lines?
Yeah. Cool lines. Okay, those are really cool lines.
That's a magnetic field. And it shows which directions the electrons spin in, like I just said. Now, electrons. You know what electrons are.
Yeah.
Right? Yeah.
I think.
Electrons are these little balls in an atom. So an atom is made up of balls.
Yeah.
Balls.
They have like 3 different balls in each atom.
There's 3 different balls in each atom. 3 different balls.
One's a positive ball, one's like a neutral ball, and then one's like a negative ball.
Yeah. We call those protons, electrons, neutrons. Yeah.
Wait, electrons are the negative balls, right?
Electrons are the negative balls, yes.
Okay.
And protons are the positive balls.
Oh, the positive balls.
And neutrons are the negative balls.
Yeah, brain blast.
In the end, as Kursiko said, everything is made of balls.
Everything's made of balls. Wow.
Everything's made of balls.
Wow. Dude, that is a revelation. Am I made of balls?
It is. You're made of balls.
Are you
I'm
made of balls? Oh,
yeah.
What else is made? Is this presentation made of balls?
This presentation is made of balls. The light coming out of your screen
made of balls?
is made of balls. Now that's actually really interesting. That's really interesting because they're not only made of balls, but they're both made of balls and they're a wave at the same time. But that's a conversation for a different time.
It's like a ball wave, a wave of balls, or balls of waves.
So actually, I'll just go ahead and talk about this. So if we look at protons, right? Right?
Yeah.
We're talking now. This is crazy. It's like what proton or not protons? Sorry, photons. Photons are light. Photons are light. Right. So we're talking about this shit, right? If we're looking at them at a given instance, and we say, "Hey, you are a ball," they'll say, "Yeah, I'm a ball." And then if we look away and we observe them in a different fashion, we'll look at them and you'll say, "No, you're not a ball. You're just like a wave." You know how we have like magnetic waves? You're just like a wave of energy. So they're both simultaneously both a ball and a wave. It's kind of crazy.
This applies to photons or?
Photons and a bunch of other stuff. But that's kind of a different topic altogether than what we're talking about right now. So.
Yeah. Okay. I'm confused, but it sounds like it sounds like if we delve into this topic, like we'll have to delve deeply for me to be unconfused, and it would probably distract from the subject at hand today. Okay. Okay. But there can be waves of balls, ball waves, or it's something that is both a wave and a ball. Okay, understood.
Yes, exactly. But for now, we're just talking about balls.
Balls.
Okay.
I love talking about
specifically
balls.
one ball. The littlest ball, the electrons. So, what's the deal with electrons, Xander? What's the deal with electrons? I'm hiding this page. What's the deal with electrons, Xander?
Oh God. Okay. Electrons seem to be. This is the way I like to describe it from what I know of. The way I like to describe it is that electrons are the balls of the atom that like to mingle.
Oh yeah.
Yeah, they like
cool.
protons and neutrons.
Cool.
They kind of like more introverted and they like to stay in their own shell, in their own little bubbles.
Okay.
But electrons, yeah, they move around a lot more and they like to mingle and make friends with the electrons of other atoms.
Oh my gosh.
That's how I learned it.
You said that. That was really cute.
Was it really
Electrons
cute?
are the hose of the atomic world.
Oh my God. Okay, the hose.
Xander,
I see.
The
Okay.
hose of the atomic world.
Yeah. Okay. Well, I
They're
guess I'm the pure one
constantly
here.
they're constantly looking for balance in their lives. They are. They're not only extroverts, they're hoes. You know why they're hoes, Xander?
Why?
Because they could be attached to this nice, lovely little atom and be like, you know what? Nah, fuck this shit. I'm gonna go to the other atom that looks a lot nicer and bigger, or maybe needs more balancing in their lives. I'm gonna go over there. Fuck this atom, and they'll leave.
Okay. So you
Electrons are made for the streets, Xander.
you can't. Why do you have to put it in such a bad light? They just like to make friends, man. I thought. Okay. So wait. So my understanding was electrons only ever moved from an atom. Like they would never leave their atom. They would just bond with another atom, or like have the electrons are used to bond two atoms. Can they actually leave from one atom to go to another?
They just fucking ditch, bro. They don't have to bond for shit.
They just did. Okay, yeah, they are made for the streets. What the heck?
They are made for the
bro?
streets. No, yes, they do. They do make bonds. Yes, they do make bonds.
Also, hi, Boomy. Thank you for the raid. Hello.
Sometimes, bro.
Yeah.
They don't give two shits. They're like,
they just
they
leave.
just dip, bro. They just
they
say I'm out.
So it's kind of like the atom is like the home of their husband, but then another atom, or rather a bigger home of a bigger husband comes by, and they're like, you know what, I like the vacation in the Bahamas, but I want a vacation in Dubai next year. And they just go to the next atom. They're like, fuck this shit.
Fuck this shit. No, exactly. Electrons are the hose of the atomic world. Yep.
Oh God.
But yeah, to run really through electrons, these idiots, they flow around the nucleus of an atom.
They're stupid. Electrons are dumb.
No, they're probably the smartest. I feel like protons and neutrons are the dumbest because they don't really do much.
I was gonna say it kind of seems like on a basic level, electrons have a better survival instinct than protons and neutrons.
Yes. As Shock said, I get around.
Yeah, they get around,
They get around, bro. They get around.
Oh my God. Okay.
They're made for the streets. But yeah. So they flow around an atom in their own energy levels, and also spin and go in different directions, all within their own energy levels around an atom. And they can jump from one energy level to another. So let's say they're like, they can be like, oh, I like being this close to the atom. And then suddenly they're like, you know what if I jump over here and another one takes my place? Yep.
Oh, so they like swap positions all the time.
Crazy, bro. No, they're fucked up. They're fucked up.
Oh wow. Is that what this little diagram is?
Yeah, well, this is just looking at energy levels of electrons. So you have the nucleus and the nucleus. So there's less electrons towards the center of the nucleus, and that's mainly because it's very it's all about a balancing game, right?
Yeah.
So let's say you have two protons at the center, right? There's only gonna want to be like two electrons or something like that. Not necessarily, but the closer you get, the harder it is for you to leave, right? So if you're really close, you don't want to leave. But the ones on the outside, those are the ones for the streets, bro. They're like, so we don't necessarily have to stay. We've got a lot of energy, and if there's another atom that's looking down and depressed, we're gonna share our energy and go over there, and we're gonna spread our wings and fly away. And then that atom will never see that electron ever again.
Kind of sounds like protons and neutrons are more loyal and they're more wifey material, and then electrons are kind of just like they're the side chicks, no commitment, low commitment. They're just here for the casual relationship.
They are. But as Mothman said, some electrons get greedy and block out the other hoes. They say, you know what? No, we're comfortable here. You don't need to be here. We'll stay.
I see. Okay.
Electrons are fickle little guys. They're very silly. They're very silly.
That makes sense.
So, why do electrons matter, Xander? Why do electrons matter? There's a lot of words on this page.
Okay, I'm gonna not look. Okay, why do electrons matter? I mean, my idea was still that they bond the atoms together, right?
Yeah.
I feel like that's one of the most important things they do. I mean, it sounds like from what you explained to me too, there's a lot of balancing in energy levels for atoms. Like electrons will do that, and maybe that's also why they split off because they need to balance in other energy.
Right. So a lot of that like balancing shit, that's for chemistry. This is physics, bitch.
Okay, physics.
So in physics, you know, I mentioned earlier that electrons like to spin. They like to jitter around. They like to move. And these spinny sons of bitches are the entire reason why we have magnets to begin with. At all. At all.
Okay.
Yeah. So the diagram below, you can see there's three boxes, right?
Yeah.
And one says diamagnetic, one says paramagnetic, and the other says ferromagnetic. So without reading, what do you notice? What are you observing with these images? I'll move out of the way a little bit so you guys can see.
Okay. Can I ask a question? Does H stand for hydrogen?
No.
Okay. Then
No.
Well, I mean for it just seems to kind of I'm assuming like the arrows will kind of display the path or the pattern that the magnetic field follows. It seems like diamagnetic is either if whatever H stands for, if H equals 0, they're all going to be still and not move. But if H is greater than 0, then they're going to move to the left. And then it's the same for paramagnetic. If H equals 0, then they're all going to be scrambling around. But if H is higher, they're going to go to the right.
Okay.
And then ferromagnetic seems to be all towards the right.
Okay.
Question mark.
Okay. So, I mean, you're on the right track. So, diamagnetic are things that are like they have weak attraction to things. So you see how they don't have any arrows on the left?
Yeah.
They have generally very little magnetic pull to anything, but they can still like, you know, nudge a little bit, maybe like
God, they're
feel
virgins.
a little.
They're the virgin electrons.
They're like the virgins of the magnet world, right? They don't like to
No
connect.
bitches?
They don't like to move around. No bitches.
Okay.
Yeah. Now paramagnetic, you see they got some magnetic force going there. You see?
Yeah, I see that.
They're like scrambling around. They're doing their own little stuff. I mean, they're kind of moving around. But they aren't moving uniformly, right? They're moving uniformly.
They're all scrambled, right? They don't have order. They don't have
exactly.
They're lost.
But now what happens to them when they do have a magnetic field against them?
They all move the right way. They all move.
Yeah.
Oh wait, I think I'm starting to understand.
Okay.
So H equals 0 means there's no magnetic pull, and then H with the arrow sign means there's a magnetic pull towards that way, right?
Yeah.
Like towards that direction.
So essentially the H is just saying like, oh, there's like either there's no magnetic field. So if it's 0, there's no magnetic like field present, and then the H with the arrow is showing like the direction of the magnetic field.
Got it. So in diamagnetic they would kind of repel. In paramagnetic they would kind of pull. Got it. So then ferromagnetic means, I would assume ferromagnetic just means they pull even stronger, right? With more.
Yeah. And now look at the direction of the ferromagnetic, like without any
magnetic field present.
Magnetic field present. Yeah.
It's going
now, what do you think about that?
Upwards and to the right.
Ignore the direction. More so, just look at like their uniformness.
I don't know. I'm just gonna say that even without a magnetic field present, they're still very uniform. Like they're still very in order with their movement.
Yeah.
Okay.
Yeah. So essentially, ferromagnetic like metals or like materials are already kind of like magnetized, but in the presence of like a new magnetic field, they'll adopt the rotation of that field. and sort of come forward. So let's say
okay.
you've got like a magnetic field going one way and stuff like that. And by the way, I see somebody in the chat asking, is this related to the right hand method? Yes.
Right hand method.
Yes, it is. Yeah. So essentially, there's a right hand method. If you stick your thumb up and stick your pointer finger out and make a gun. And now take your middle finger and just point it straight outwards off like your knuckle. So you've got up, forward, and left, right?
Yeah, up, forward, and left. Okay.
So this is just a thing in physics. The idea behind this is that you have your magnetic field going forward off the gun. You have your current. You have your current coming off the middle finger, and then you have your thruster motion going upwards. So.
Oh, they're all kind of like pulling at each other.
They're all kind of like they're all related, but they kind of dictate how the magnetic field works, right? So like if the current's going, like let's say the magnetic field is going forward and the current's going to the left, that sort of determines the direction that magnetic field is going to pull toward. Yeah.
I'm lost. I'll be honest.
It's okay. No, that's fine.
I just look at my hand like, what does this do?
It's fine. No, it's fine. Because right now we're interested in the paramagnetic and the ferromagnetic like materials, right? Because they both like to be around magnets. They like being magnetized. Bam! Okay, bitches, let's talk about magnets within electric field. This is literally what I was talking about with the right hand thing, the right hand theory. So remember that we said magnetic fields were caused by electrons spinning in a certain direction, right? Right. Well, what if I told you we could change the direction of those spinny little fuckers by having them interact with an even stronger spinny motherfucker?
Okay.
Right?
Okay.
So, Faraday's law of induction.
Blah, blah.
I'm just going to say that. Yeah. Blah, blah, blah. Don't need to talk about it. But essentially, if a magnet moves through a copper coil that has an electric charge, the charge will change the magnetism, right? So let's say if you see that on this image right here, and see on the image, we have a like a magnet that somebody's holding. You have it the north, you have the south on the bottom, and then and then he's holding and so remember how we said that there's the up, which is the thrust, right? So you've got the thrust of your point of your thumb going up. You have the magnetic field of your pointer finger going out, and you have the charge of your middle finger going to the left, right? Right?
Yeah.
So we're thrusting this big ass magnet up into the hole of the coil, right? We're shoving it in the hole. And then this magnet, so, oh God, right. So,
non-sexual, by the way.
Non-sexual. We're talking about magnet going into.
Shoving through a hole. Through the coil. Coil, yes.
So it says I there with an arrow. What do you think that means?
The eye there with an arrow, I think that means that the magnetic force of...
It's not magnetic. Look at the galvanometer and then think about what it's saying.
Galvanometer.
That's just on the page. It's okay.
I think I want to say that the arrow dictates like which direction the
what's the middle finger? What's the middle finger? You have it.
The current?
Yeah.
It dictates like the direction the current is traveling through the coil, right? Okay.
Okay, you're getting it.
Okay. So right now it's going from the right side of the can you say galvanometer? Okay, it's going from the right side of the galvanometer, and then coming back on the left side, which like where the arrow Okay, I'm starting to get it.
Okay, you're getting it. Okay, cool. So, if we're shoving it up into the galvanometer, and then we pull it out of the galvanometer, we can change the direction of how the magnetic field is like is like moving, right? So look, you see how it says like, oh, he's going up and he's just like going up and out and up and out in that hole, right?
Yeah.
Yeah. And if you see with the south, you can see the south is showing like the magnetic field going inwards.
Okay.
Yeah, meaning it's like a quote unquote positive. Usually you say positive if it attracts things, but quote unquote positive.
Okay.
Yeah. And then you can see how if it's stationary, you have like your direction being 0. So moving on, because I can see mine's breaking a little bit. It's okay.
I think I'm just trying to understand. I feel like so. I guess what I'm confused by is I think basically the images are trying to show you that the person is bringing the magnet with an upward force in the first one and downward force in the other one, right?
Yeah.
And is it the force that's causing the current to go?
It's causing the charge. Yeah. So the force, so the galvanometer is measuring the electric charge, and so by moving the magnet upwards into it, that magnetic field is causing a current to go into the coil to start in the coil, and it's going in the direction of that charge. So now you see how he's pulling it out and the charge is going to the right.
Yeah.
And what the magnet is showing on how it shows the south side going up, you see how the charge is the same if the south side is going up as when the north side is pulling out. So that's just showing the direction of the magnetic field
of the magnetic field.
How,
okay.
Yeah, how like the reasoning behind why there's like a north and south end, right?
Got it. Yeah, I think what confused me at first is I assumed the output was determined by the galvanometer, but the galvanometer is recording. It's measuring. Okay, that makes sense.
I think that was my bad. That was my bad. Yeah.
No. I just didn't understand because this is so big brain stuff.
Yeah.
Good night, Abby. Good night. Bye. Okay. So, and don't apologize for being late, anyone. We're in the middle of the lesson. I'm sorry if you've missed anything. You can watch the this VOD later. It's going to be on Canvas under our class section.
The class section. Just make sure to navigate to the correct page and then make sure to pay your tuition as well.
Exactly.
If you don't pay your tuition on time and if you're still messing with the feed deferral, you might not be able to access the material. But make sure send it to jun.akane@notascam.net.
Yeah, I like it. I like the way this guy's singing. So. We like how what we're seeing with the magnets, right?
Yeah.
Okay. Let's go on now to the cool floaty part.
Okay,
right?
The cool floaty part. Okay.
The cool floaty part. So, changing a magnetic field causes the magnet to hold electric current, right? When we go into the coil, it causes electric current, right? We see that. We know that, right?
Yeah.
So, if we change the direction of a magnetic field, so let's say we have a north side magnet and a south side magnet, and we turn it so that way both sides of the magnet are like north and north, right? By inducting a current to the magnet, we can change the direction of the field. It's kind of like works the same way. So
confusion.
You get it. Okay. So
how are we changing the I must have missed it. How do you can you just briefly touch on how you change the field of it?
Going back.
Yeah,
So doing this with the magnet, right? We're going into the hole. We're going into the hole, and it's inducing charge. Now, what happens if you induce charge on the magnetic field?
If I induce, so I think what I'm understanding is that basically. Okay, I think what is going on in my brain is you're saying as we bring this magnet through the coil, it changes like the south end to have the same field as the north end would.
So the image right here is showing how if we put a magnet through a coil, we can induce magnetic charge or like electric charge, through the coil. So the coil is copper and the coil has electricity. And the magnet can affect if there's electric current going through that coil. Now, inversely, if you have a magnet and you put that magnet into a coil and put electricity through that coil, you can change how the magnet flows.
So okay. So the coil has electricity in it, and it changes the south end to have the same attraction as the north end?
Yeah.
Okay, okay. And then once you remove the coil or the magnet from the coil, then it goes back to normal? Or does it change permanently?
So it's like a temporary thing for depending on how it's done, right? So excuse me.
Yeah, no worries.
Yeah, so so you can in doing this you can not only change the charge of the magnet, but if you wanted to, you can either completely get rid of the charge of the magnet so that the magnet is just done, it doesn't magnetize anymore, or you can induce a charge on the magnet. So you can basically, using electric current through this coil, you can make it so that way the magnet is like dead, or you can make it so the magnet is like super positively charged or super negatively charged, right?
Got it. Okay.
And then that also changes which direction the electrons are flow spinning. Yeah, because remember the magnets have to do with electrons. Yeah. Okay.
So for in this example, so in this example, like all in the south end or in the north, like in the north end, electrons are coming out of it. In the south end, it's coming into it, the magnet, right? So it's pulling. So basically, you would kind of reverse that when you put the electricity through the coil. So then the south end would be repelling as well.
There you go.
Got it. Okay. Naruto.
It's kind of like that. It's kind of like that.
Okay.
So.
Okay.
Changing the magnetic field actually causes the magnet to hold an electric current in the magnet itself, right? Because when you're changing the magnetic field, you're putting a bunch of electrons around the magnet, and in doing that magnet is usually made out of some type of metal, right? And metal's like conductive, and so it's got a whole little bit of electric charge. Now that electric current is actually called a Gary current, I think.
Gary current? Why Gary?
Gary current.
Like the pet snail from SpongeBob.
Let me see. Current. Gary or Gary? Regardless. Regardless, yeah, it's like a Jerry current thing. Eddie, is it Eddie? It might be Eddie current. Hold on.
Eddie current.
I know it's something.
This is definitely named after somebody who discovered it, right?
Eddy current. That's it. Thank you for correcting me because I didn't write it down and I knew it was like E something, right? Yeah. So eddy current, right? And that is basically a swirling electrical current, created through conducting the metal, such as copper, and moving the metal through a magnet. Okay. Right. So cool. And Gary, I'm sorry. Cool. It's Eddie Gary is close enough.
Eddie Gary.
Yeah, cool. So these eddy currents, right? These eddy currents are usually very, very weak. Super weak. Okay. And with the resistances of most metals and temperatures and stuff like that, they'll dissipate very rapidly at room temperature. Now, what if I told you if we get this shit cold enough, there are no resistances?
This is where the nitrogen comes in, right? Okay, wait. So just to touch it really quickly. So adding these currents, these eddy currents, that's what running the electricity through the coil will do to the magnet, right? It adds those currents. Yes. And that's how it reverses the field. But usually it doesn't. It's super temporary, and it usually doesn't stay, at least in regular temperatures, unless you freeze the metal. Yes. Because okay. Yes. All right.
Yes. Now I'm gonna blow your mind a little bit, right?
Okay.
We're gonna blow your mind a little bit.
Yeah, blow my ball. I mean, my mind.
Now entering the superconductor. Now what is a superconductor, Xander?
Oh shit. Okay, so I'm gonna use context clues. I'm gonna assume that metal is conductive, right? Yep. Probably when you know nitrogen, you get metal cold enough, it becomes a superconductor because of the lack of resistance.
Okay. He's learning. Right.
And it holds those eddy currents very well. Question mark.
Yeah.
Okay.
Yeah. Now, what does that do to the magnetic field?
Reverses it. Right.
Yes.
Or makes it stronger.
Yes.
Depending on where, depending on what you do to it, right?
That's right, Xander. They conduct super hard.
Wait, there's no way. This kind of this is actually a really sweet like card for you to put in because it shows that you like know me. It shows that you know I would have gotten something out of this. That's actually really cute. Wait, I really like this. Oh my god. Okay. All right. Wow. Okay.
So now let's go into it. So basically, you can technically, quote unquote, cool any conducting material low enough, and it'll become, quote unquote, become a superconductor.
Yeah.
But some are a lot easier than others.
Okay.
Now, at room temperature, conductors allow magnetic flux, which, not to confuse your brain with a new term, but magnetic flux is basically these rays of electrons coming off of the
lines I illustrated.
It's the lines,
yeah.
It's basically, so you have a magnetic field, and the field is what we're seeing here, and each individual line there is what is called magnetic flux.
Okay.
So, yeah. It's the I even wrote it there. A given number of magnetic field lines to pass. So it allows the magnetic flux to pass freely through the conductor's atoms, right? So normally when you have like a conductor with a lot of resistances, the fields kind of have to like go around it, right? Can't like go directly through it. Kind of has to like go around, and that's why we see with this image. We see it's like, oh, it's coming around, right?
Yeah.
Okay, cool. So when these bitches are cold enough, the conductor basically gets a JoJo stand that punches the magnetic flux away from them.
Okay.
Okay.
So,
enter the Mesner effect.
what is the Mesner effect?
Okay. Yeah, I know. Okay. The Mesner effect.
There's more.
Right?
But there's more.
So we talked about Faraday's law, right? So now the Mesner effect. So the Mesner effect, basically, we no longer fuck with magnetic flux anymore.
Okay.
So superconductors, after getting to a certain point, once they go below a certain temperature, remember we said they're superconductive. If they go below a certain temperature, they now start repelling the magnetic flux from the inside. So all those Eddie's
waves, current, eddy current.
Oh, fuck, what did we call it? Eddy current. Yeah, eddy current. Right.
Okay,
all those eddy currents, they say, fuck the magnets. We don't like the magnetic waves going through us. So we push them out, right? We push them out. So if here we say, okay, look, so the temperature T is just the normal temperature, and temperature C, which is the critical temperature at which the superconductor will start saying fuck magnetic flux, will say, okay, we don't want you coming through us. We don't want you coming through us.
Yeah.
So let's talk about impurities now. So when you have a metal, right? You know what a metal alloy is?
Oh god, a metal alloy? No.
Okay, it's just like when you combine two metals, right? And you make a new metal. So think of it like this way: you have
like bronze or something.
Yeah, exactly. So bronze is a mixture of copper
and tin.
I think so. Yeah, okay. So copper and tin. That's like a metal alloy kind of.
Okay.
Loosely, kind of. Because of that, it's going to be impure, right? Because sometimes you have these things and they don't always 100% mix all the way. So you have bronze that's like really good bronze, you have bronze that's really bad bronze, right? So just like you or I, impurities in a superconductor are important for these magnetic hating boys to float. These superconductors to zip up and down, right? So essentially, if you have impurities in a superconductor, some parts of the superconductor, when they get really cold, will say "fuck magnetic flux." Me and my boys and my homies hate magnetic flux.
Okay, yeah.
And then other parts who don't have those eddies, like eddy currents in it, will say, magnetic flux so good, tasty, Yeah. And they'll eat up the magnetic flux like crazy. So you have these really small condensed sections of this magnet that are letting this magnetic flux go through, and then the other parts of it are saying fuck the magnetic flux and not letting it go through.
Yeah.
Okay.
And I think I just want to ask, like the reason this is probably due to like different materials having different freezing temperatures, right? Is that what causes it?
Yeah,
Right?
kind of,
critical temperature or whatever,
exactly.
right? So like the copper and tin would have like the parts of the bronze that are still more copper or more tin will have a different freezing temperature than the rest of it, kind of.
Yeah.
Got it.
We're just using bronze and tin as like an example. Those aren't really good superconductors. Like bronze isn't a good superconductor at all.
Got it. Okay.
You have to. Oh my god, I know the elements.
What is a good superconductor? Steel.
Oh god, no. There's
Iron.
what is it? It's a
Copper.
No. It's like some crazy alloy.
I remember hearing copper was like a really good conductor though, no?
It is, but it doesn't make a good superconductor. Oh shit, what is it called? I tried buying it not too long ago.
Oh, for like an experiment for this, like this.
Literally this. No, literally for this to try to get liquid nitrogen to make this shit float. Oh god, what is it called? Okay, hold on. What is it called?
Question.
Yes.
While you're searching that up, for those who may be watching the stream and be interested in trying this for themselves, how dangerous is liquid nitrogen?
Okay, so when I tried doing this in high school, liquid nitrogen is at 77 it basically is so cold that it makes a gas into a liquid. And if you get that shit into my, oh my god, KF16 found it. Okay, so if you get that shit on your hands, you'll basically instantly frostbite and like your fingers will be gone. So it's very easy to control because if you could, it's just like a water, right? You just pick it up in a like a scoop thing, and then you can pour it, but you don't want it near any part of you. I'm sure some of you guys have seen. Yeah, I've seen stuff like do not drink, you'll die. Thank you.
Don't drink
you guys
it.
have seen
Do not drink it.
experiments. Well, they'll take like a balloon, right, and they'll blow the balloon up, and then they'll dip it in the liquid nitrogen. It'll freeze, and when they pull it out, it's like a rock, and they can like shatter it and stuff. Liquid nitrogen is extremely cold. Okay, so the one I was actually trying to buy, KF16 found it, is yttrium barium copper oxide. And the reason why this works really well with liquid nitrogen,
like a bunch of different metals combined.
It is
right?
a bunch of stuff combined. It's like
Barium,
a really crazy
copper,
alloy.
Yeah.
And so essentially what happens with this alloy is that its critical temperature is I think 77 degrees Kelvin, which is easily attainable for liquid nitrogen because liquid nitrogen is very, very cold. And for those of you who don't know about Kelvin, Kelvin is a degree, is basically looking at temperature at an even smaller scale than Celsius
or Fahrenheit.
Yeah.
Right. Okay.
We look at Celsius because in sciences, you want to look at Celsius because metric systems always used in science.
Yeah.
But to put it simply, 0 degrees Celsius is 273 degrees Kelvin. So if you have 77 degrees Kelvin, that's negative 196 degrees Celsius. It's extremely cold.
Extremely cold.
It's super cold.
I like the coldest winter in like Canada, which is like everyone knows Canada's like really cold. The coldest winter in Canada is like negative 40 or something.
Yeah.
That's like the coldest winter ever.
Yeah. So liquid nitrogen is that 77 degrees Kelvin. And so a lot of these, it basically is cold enough to cool these superconductors down to allow them to be like at their critical temperature. So KF16 said in chat, the critical temperature is like 90 to 95 Kelvin. So it's below enough by a certain degree that it can guarantee get it to that point where it has that superconductive properties.
Got it.
So basically, the flux will enter these impure spots and get stuck there because they can't enter the anti-flux maxing part of the conductor.
The anti-flux maxing.
I don't know if you've been realizing. I've been trying to make this as like.
I've been like, I kind of just ignoring it, but like I'm like, bro, you're trying to put like the Zoomer lingo in like the.
I'm trying to make it as easy to understand.
Oh my god, anti-flux maxing, dude. Oh my god. Wait, I just want to ask you a quick question. Like in that video, right? Because you said like liquid nitrogen is very dangerous, but in that video, that guy was still touching the disc that you showed in the video with his bare hands. How come that's possible?
So how do cold things and hot things work? When things that are really, really hot, okay, so an atom moves around a lot. Everything jiggles, especially the electrons. Electrons move really fast, right? They're really, really fast. They move a lot, and the protons and neutrons that are connected to each other, even though they're like really, really close and bonded together, they still kind of like jiggle around and stuff, right?
Okay.
Well, when something's really, really, really cold, those electrons and protons and neutrons slow down a lot. They get really sluggish and really slow and stuff like that. And so if you have a something that's really, really cold, and you could do this inversely with things that are hot as well. So let's say you have like a hot piece of food, right? Or like somebody throws a hot loaf of bread at you. What do you do with that hot loaf of bread?
I would
If you
like
don't want
kind
it
of
to burn you.
I'll kind of like. Well, I mean, if someone throws at me, I'm gonna dodge it. If it.
No, but if let's say something that you want to eat, but
Yeah.
Hot
It's
potato. You know, the game
you
hot
play like hot
potato?
potato, right? You kind of like bounce off your hands a little bit.
Exactly, bounce off your hands.
Yeah.
Yeah. So it's the same idea with cold things. If you have something that's really, really cold, it won't burn you if you move very, very quickly around it. So it won't like make you freeze. It'll just feel really cold in your hands as long as you keep moving it around. It's like an ice cube. You know how if you ice cube on your hand?
Yeah.
If you leave it at one spot for too long, it starts hurting. That's because it's literally freezing your hand.
Yeah.
So if you move it around a lot, it doesn't hurt, but you still get that cool, nice, icy feeling in your hand. Same principle with super, super, super cold things.
So that guy was just touching it like for a short amount of time.
He's touching it very short, and he's also moving a lot when he's touching it. So it's not like he's not letting himself stay in one spot for too long and getting frozen.
If he just like held it, his hand would probably start freezing.
Exactly.
Gotcha.
Oh, gotcha. Gotcha.
Yeah.
Okay, I get it.
Okay. So basically, these fuckers can't make up their damn minds about if they like magnetic fields or not. And because of that, you have one side. Remember how we said diametic earlier? It's like, here, I'll go back.
I remember that.
Diametic, which they don't like magnet, and then we have paramagnetic and ferromagnetic. They really do like magnet, right? So at this point, you have part of this superconductor is super diamagnetic, so they repel everything. And then on the other hand, you have these super, super small impurities that are super, super magnetic.
Super like ferromagnetic, right?
Super ferromagnetic, yeah.
Okay.
And they'll let the magnetic flux pass right through. And so, because of this, a superconductor repelling just enough of the magnetism, it allows it to float in space, letting the impurities lock it in the air. Yeah. And this is what we call quantum locking. Because at this point, this object is quite literally, as long as it stays cold and stuff, frozen in space.
Yeah, frozen in like it's just not
it
gonna
is
move.
locked in it's locked in its position. So even if you push it around a track, like earlier we saw that video of them that guy pushing along a track, it stays in the same orientation. So you can like move on its side, move it upside down, all that stuff, and it'll stay in its orientation, but you can still move it along the X and Y and Z axis. So it moves around.
Yeah. Okay.
Yeah. What do you think so far of quantum magnetic levitation?
It's starting to make sense. Like I think the thing that's awesome is that it's actually starting to make sense, right? Because it's the because I always thought like, well, I guess it's impossible to avoid impurities in any kind of alloy. But yeah, I guess it makes sense that like it's, and this only applies like the object will only float if there's also an outside magnetic force acting on it, right?
Yes.
Yeah.
You're so good.
Because even if you have a superconductor and you just put it on like a plain wooden table, it's probably not gonna float, right?
Not gonna do anything.
Yeah, it's not gonna do anything. Yeah. Okay.
That's one of the reasons why I was asking you to observe early in that video, because one of the things on that video, if you looked, everything that guy was placing his superconductor above was a little tiny magnet ring or like a magnet plate.
Or that like magnetic table track thing, right?
Yeah. And that's what lets it float. Yeah.
And that's why it would follow a certain like track or like, direct, like it stayed in a circumference. It stayed in a certain circumference. It didn't go outside of it. Yeah.
Exactly.
Okay.
Isn't that cool?
Yeah, it's really cool because that also makes sense as to why when he just like, pushed it along the track, it didn't go outside the track because, well, like there's enough, what's it called? there's enough impurities to keep it connected, but the rest of it is diagmatic, so it's keeping it off of, you know, sticking to the track.
God,
so it's kind of like I get it. It's also why I stayed upside down.
That's so cool, right?
Yeah, that's actually really cool.
So let's go watch a video of how, because one of the things I want to talk about is like what we're trying to do with this sort of technology in a real world environment to make it into something practical, right?
Yeah.
So let's go and look at this. This is another video of this like liquid nitrogen superconductor on a track, right?
Yeah.
Do you see he's putting paper underneath it to show that it's literally floating, right?
Yeah.
It's not making contact with the magnet. It's not touching anything. And he has a motor hooked up to it.
This is
and this
necessary.
little motor
Joint between two magnets. It
basically allows it so that way once that superconductor passes through it pushes it along, so it gives it some energy, right?
The motor is supplied by a DC
Right.
power source.
Okay, so now you can see it's like going, and if depending on how much electricity they put through those motors will defend how fast this little superconductor will go across the track.
So those motors are it's generating electricity that's going through the magnets that it's connected to.
No, it's literally just like two wheels. It's sort of like how like a roller coaster works. You don't have wheels on the track. Those wheels push the roller coaster along. It's just like that. Because with the superconductor, all it can do is float alone by itself. It floats really, really well, but it can't move itself. So you have to put a force onto it to move it.
So I think, okay, so this is where I might be getting confused in this explanation.
Okay.
Wait, hold on. No! What happened? Why is it no?
Just because it was just like a out of sound effect.
Oh, okay. Because I think what I'm getting confused by is what you're explaining is, or what I think you're explaining is that those motors are applying a physical force to the conductor.
Yes.
And so if the motors were running, but the conductor started on one side of the track, it would just never move, even if the motors are running.
Yeah, because it's not making physical contact with it. The whole thing is that those motors are just to push it along, to show the transfer of energy, right? Because you can't make something do something if there's no force applied.
Got it. Okay. I think I understand. I think maybe my misconception is that I was thinking that it was some kind of electrical stuff, and it was like super.
Yeah.
So I was. What is it called when you expected something to be more complicated than what you see?
Yeah.
You know?
No, I don't know the word, but I know
what
you're talking about.
I was expecting like, that motor isn't actually touching the superconductor. It's like applying some kind of energy into the track, and then the track is. That's what I thought, but it's just pushing it. Yeah.
So ideally, the cool things that we can do about this, or do with this, and now remember, the videos I showed you were from like 2011. These were like from 14 years ago, or 13 years ago. I can't math. 13 years ago. It's a long time. Now, in that long time, the idea of what we've been looking for is that, remember, we've been trying to make this superconductor, and the only way to get the superconductor to work is if it's super, super cold, because it has that critical temperature, right?
Yeah, the critical temperature.
Okay. Yeah. Now, what we've been trying to search for is finding a conductor that we can make
at room temperature.
We can have that superconductor at room temperature. That's the idea. We want to be able to make sure that its critical temperature is that whatever, like 89 degrees Fahrenheit.
Like that people can live in, so that it has real world applications, right?
Exactly. So that way we don't have to cool it down. We don't have to cool it. We don't have to do anything that would be excessive. We can just make it so that we have these super, super efficient, like non-resistant based, like levitating metal plates that we can push along. And now the ideas with this is that in application, if we want to, we can make like super, super fast like trains and stuff with this. You've been to Japan? You've been to Japan?
Yeah, I've been to Japan, yes.
You know the bullet trains that they're like crazy fast, right?
Yeah, they're so cool.
Yeah. Now, do you know the technology behind the Shinkansen?
No idea. No.
Magnets!
Is it magnets?
Magnets! It's electromagnets. Essentially what they do is they propel it along this like really, really fast using magnets. They push the electricity and it goes zoom, and that's why it's so fast, because it has very little contact, and so it's able to move really, really quickly and stuff.
Okay.
Yeah, they use magnets. So the idea is if we can get something, because that still has resistances and stuff, and it needs anything will need electricity ideally. Or realistically. But if we can get something that's a superconductor where it needs very, very, especially at room temperature, it needs very little stuff. They can just do this. They can make it go really fast
yeah,
because
they
it
can
has
make it go-
very little resistance.
Yeah.
So it can move really, really quickly.
Would that affect like passengers inside of it if it was moving at this speed?
You've been in a train before, in a super fast moving train. How's it feel?
You're right. It just kind of feels. I mean, I feel like some. Well, I mean, you only really feel the force of when the train starts and when the train stops.
Exactly. So ideally, because you're. It's not like it'd be one thing if you're moving at one speed and then like you stop really abruptly, right? You're gonna go flying.
Yeah.
But that's why you make sure that these things aren't like super accident prone.
There's gonna be a lot of testing, a lot of to make it actually.
Of course, and
Okay.
obviously we still haven't found a superconductor that is
that can operate at room temperature. God, okay.
Liquid nitrogen, like we were saying, is super dangerous, and also it's really expensive because you have to get it. You have to get the liquid nitrogen cold enough. Now, how do we get liquid nitrogen, Xander?
Shouldn't I know. I don't know.
Remember how we said that we have those atoms, right? And those atoms are moving really, really fast when they're hot, and when they're cold, they're really, really tight and very slow moving. Well, essentially what we can do is we can induce temperature. We can induce the temperature to be smaller by making it so that way those atoms have a lot less space to move around in. So we basically just compress nitrogen. We make it so that it has a really, really, really high pressure.
Oh, is that how it works? Okay.
Yeah.
It's kind of like, hold on, because I'm just trying. Okay.
You compress it and you cool it at the same time, because so that way it's like
okay. Because I was like, because like what I understand of compressing things, the only thing I know is steam, steam in a boiler or something, and it's like it's compressed in the boiler because of liquid becoming a gas expands in volume by like a bunch of times or whatever. But because of the tank of a boiler, it stays compressed. Is that like that's kind of how it is in liquid nitrogen? So it becomes a gas, but then as it's becoming a gas and expanding, they cool it or.
No, you're right, because you're talking about the like steam.
Okay.
With liquid nitrogen working opposite, because at room temperature nitrogen is a gas, right? And so if we cool it and compress it at the same time, we can eventually get it so that way it's below the temperature of that evaporation point, and eventually it starts condensating, just like water vapor works, like how we have clouds are just like condensated water, and then once it gets super condensed, it turns into rain and stuff. It's the same idea, except with nitrogen instead of water, and we're just adding like pressure to make it happen.
Okay. Brain is expanding. Physics. Wow.
Physics. Wow. Okay, so now because I really want you make you think. Remember how we talked about quantum earlier, right? Where we were talking about that word quantum.
Yeah, quantum.
I added some extra stuff at the end here that we can touch on, because I figured we'd get through this a little bit quick, and this will give us some more talking points if we want to get through a little bit. So there we go. So quantum physics is crazy as shit, right? It's crazy shit. Now, here are some other ridiculous things that happen in the world of quantum physics. So we have quantum leaps. Now, quantum leaps is when an electron moves from a higher to a lower energy level and emits a photon of light. And this is what we call a quantum jump. Now, the idea behind this is that it's, you know how electrons are negative energy level, right? And we showed earlier, if we go all the way back, we showed earlier that they have these energy levels, right? Now it's really easy. It's really easy for an electron to get to a higher energy level, but losing energy is really hard.
It's really hard. Okay.
And so the only way for it to lose energy is to make energy of something else, because there's the conservation of energy and conservation of mass, right? Mass, right? So
conservation of energy and conservation of mass.
Yeah. So
I don't know what those mean.
So energy. So mass cannot be created or destroyed, right?
Okay.
So there's finite amount of mass in the world, right?
Yeah.
So let's say you take a piece of paper and you burn it. You burn it. the
Yeah.
same amount that mass, however much mass was in that paper, when you burn it,
It became smoke.
it'll turn into smoke. It'll
Yeah.
turn into ash. It'll turn into a bunch of different things, but the mass, like the total number of
Yeah.
mass it has, will stay the same.
It was still the same. Okay.
So yeah, that's the conservation of mass, and the conservation of energy is kind of similar. So we have kinetic energy and potential energy, right? Potential energy is the idea that it has the potential to have a lot of energy, basically.
Yeah. Yeah.
So if we hold something really high, it has a lot of potential energy because as soon as we drop it, it's going to start pulling down because of gravity, right?
Yeah. Yeah.
And kinetic energy is something that is already in motion, right? It's like something that's already like, if you're running, you've got a lot of kinetic energy because you're
Yeah,
using
yeah,
the
yeah.
potential energy, right? So the idea behind this is that if it jumps from a higher energy level to a lower energy level, that energy has to go
Has to
somewhere.
go somewhere.
It has to go somewhere.
Yeah,
And so
okay.
then basically as a way to for balancing, it creates a photon. It spits that boy out. It's and the photon comes out.
Okay. Okay.
Yep. Pretty cool.
So you're saying like the electrons, when they go to a different energy level, that's the when they spit a photon out, right?
Yeah, when they
Got it.
they go from a higher one to a lower one, because going up to a higher one is really easy. Going from a high to low is hard.
Okay. Okay.
They
Okay.
have to eject that proton. They have to spit it out.
And so photon is
Photon.
light.
Yeah.
Mark?
Yeah,
Okay.
photon is
Okay.
light.
So when we have things that emit light, that is an electron constantly going to a different energy level and spitting out light? Question mark? Or is there no correlation there?
Kind of. Not necessarily. So visible light is like, it is like a photon.
Okay.
But it's like
Okay.
a bunch of photons. It's a bunch of photons.
Okay, so we're talking about something that's not visible to the human eye, right?
Yeah,
In that case, the
basically.
photon? Okay.
At this point, a photon is basically like a unit of electromagnetic radiation.
Got
Like
it.
you know how light from the sun, we have like different rays. We've got like UV rays and
Yeah,
visible
yeah.
light rays and stuff.
Yeah, yeah.
Those rays are made up of photons.
Got
So
it.
it's like they're really tiny. I mean, electrons are tiny, but photons are really tiny.
Or even smaller. Okay.
Yeah, they're really, really tiny.
Yeah.
Yeah.
Okay.
So basically, you're right. Yeah, like light is photons.
Okay, but it's in this case, it's like so small that like when an electron emits a photon to go to a different energy level,
Yeah,
that photon
yeah,
is
yeah,
so
yeah.
small that it's like not something that we can see.
Yeah.
Yeah. Okay.
Yeah.
Okay.
Eventually, we can see it because there's like a bunch of photons. Yeah.
Because it keeps, they just keep doing it, and they all converge. Okay.
That's why like you know how they have like I guess the particle colliders is kind of an example. You know, when we clash particles, it creates a lot of energy and it makes a big bang of light.
Particle? No,
Okay.
I don't know what. But, okay.
So there's this really cool tunnel thing called the Hadron particle. I think it's Hadron. Hold on, particle collider. I think it's the Hadron Hadron particle collider. It is a 27-kilometer ring of superconducting magnets. Superconducting magnets. What we talked about earlier.
Yes. I understand.
But essentially, we spit a particle on one side of it. And it starts going really, really fast because it's getting a lot of speed from those electromagnetics, basically making it super, super fast. And then eventually we throw another particle in it. And the goal, and I say another, we throw a bunch of particles. But because particles are really, really small, it's hard to kind of hit them together.
Yeah.
Unless they're going super fast. So we throw a bunch of particles on one side and we throw a bunch of particles on the other side. And we make them go really, really fast and we try to slam them together. They go bam. And then when that bam happens, we get a bunch of energy being like popping in one spot. And it makes and all of that happening is that light we see is from the photons being emitted from that quantum leap sort of idea.
It. Okay,
Yeah.
so
it's like
I want
particle popcorn basically.
Is that like also what would cause? I'm trying to. I think like what would help me understand the most is if I can relate it to something that I've seen before. So like for example, and what I'm thinking is, for example, you know when you hit like flint and steel together,
It makes like sparks.
It makes like sparks. Is that photons?
Yeah, I mean light is photons, but
like, is that caused from hitting the flint and steel, and the heat generated from that, is that causing electrons to go to a different energy level?
Yeah, so exactly. The heat
and those
is
photons,
what's causing. Yeah, you understand. Yeah, so the heat is what's causing that to be like you're striking it, and the strike is causing pressure and friction. And that pressure and friction is energy. And when it hits that, those two, the flint, basically is like, ooh, this shit too hot for me. And so it starts burning up really, really bright. And the brightness is from the photons being emitted from the electrons getting really, really hot and compressed.
And does that cause electrons to jump down levels? Is that a result of the photons a result of that?
Yeah. But usually when we talk about like quantum leaps, it is like unprompted. It is unprompted. That's why it's such a crazy thing, because with like light, with like, let's say a light bulb and stuff, we're looking at like electric that's like really, really hot and stuff. Like we're heating coils and stuff, and it's making light. Or like with like that flint and steel, right? You know, we're striking it and it's creating pressure, which creates heat, and there's friction, which also creates heat, and that's what's causing the light. But with quantum leap, it is quite literally, this bitch is just tired of being too energetic and just spits out a photon.
Oh my god. Okay. It just happens out of nowhere. Photon. It's just like
baby making photon. Yeah.
Baby making a photon. Okay.
Yep, we're baby making a photon. Just photons there. And
so it's like,
for the longest time, we didn't know this happened until we were able to observe it like once or twice, and we're like, whoa, what the hell? What's going on here?
Yeah. That's interesting. So it's not caused by any kind, because I know, from what I understand, like the basic things that I remember learning is that, you know, a difference in temperature will affect how fluid electrons can move, or how atoms can move.
Since the very beginning.
What was that?
I'm pulling a video. Because I think it's
okay. Yeah, because what I remember learning is that, you know, a high temperature that changes the change in a state of a material from, like, you know, solid to liquid to gas is due to a higher temperature and heat, and the higher temperature and heat is what allows electrons to be more fluid and moving around an atom.
Exactly.
And that fluidness in motion is what makes the change in state, right?
Yeah.
Okay.
And a lot of that change in state is from the electrons like wanting to because remember, atoms, like, so let's say we have like those like elements, right? Those elements don't really change state too often, but they make other things by combining electrons and bonding together to make a new like thing. That's like how we're talking about water. Like, we've got a random little oxygen floating around,
and then
these
two hydrogens
say, oh, we wanna you look like you could use
some friends,
electrons, so we want to be friends with your electrons, and so they bond together.
Got it. Yeah. Okay. But then these quantum leaps are unprompted. Like, there's nothing changing the temperature. It just happens.
It's just like whoa, what the fuck? Why you do this shit? What's going on here?
What's going on here? Where? Go on where?
Yep. I'm looking here. So the first cause of the quantum leap is a wave passing through two or more like spin aligned protons.
Spin aligned protons? What that mean?
I think I'm gonna confuse myself if I read any more into this. Okay. But remember how with like magnetic fields we were talking about how electrons are spinning in one direction? That's what it means, like spin aligned.
Spin aligned. Okay, so they're spinning the same direction.
Yeah. Okay. I'm gonna stop looking into quantum leap. I'm gonna confuse myself.
Okay. Fair.
I'm gonna confuse myself. But this next one's really cool.
Quantum tunneling.
Quantum tunneling. So electrons and other objects can pass through potential energy barriers that would normally be impassable. So think an immovable object meets an immovable wall meets an unstoppable object, and then all of a sudden that object just happens to like it's suddenly on the other side. How the fuck did this happen?
And it just despawns and spawns on the other side.
Exactly. So a good idea of this is like, so normally if we were to run into a door, we hit the door and we'd be like, ow, I hit the door, right?
Yeah.
But there is an exponentially finite chance, and I mean it's like super small, that you could quite literally just pass through the door to the other side.
Yeah.
Because all of your atoms every single thing, all the way down to your electrons, your protons, and neutrons and stuff, would just miss each other, and you'd go through it to the other side. And that's the idea behind quantum tunneling. So it's just like an impossibly low chance that something can like pass through something it shouldn't.
Ah.
Yeah.
Ah.
Yeah.
That's probably why sometimes, like, you know, I'm catching like a baseball or something, and for some reason it just goes through my hand and I didn't catch it. Totally what happens. Yeah, I didn't miss. I thought I caught. I mean, I did catch it. Just went. All the neutrons and protons missed.
Yep. Another idea is like, okay, so like just to put another example out there, let's say you have like a piece of wood. Piece of wood, and you have a ball, and you're bouncing off of that piece of wood. There's like an exponentially finite chance. Exponentially finite chance, just like you said with your hand, where that ball just goes through the paddle, and it's like, what the fuck? Now, obviously, this is on such a super tiny scale because it's at like the level of like electrons and stuff. So it's like very hard for us to actually be able to say, oh, this could happen. I mean, because it could happen, but there's no way we're ever going to visually see it happen. It doesn't happen at people scale, but it happens very super small, especially when, like Pixie said, when we're designing like electronics and stuff like that. So when things are super tiny, things can happen. But the reason why it's quantum is because it's measurable and we can see it in a quantity that we can measure and stuff. So very interesting.
Got it. Okay. This one I understand. I don't need to ask any questions. Okay.
Now, quantum entanglement is something that I don't know too much about, but I thought it was super interesting, so I brought it here. So let's say we have two particles that are linked together now. So let's say for example, particle A really likes particle B. They like each other so much. Yeah, they go on a date. They hold hands with each other so much that you physically like cannot understand which is particle A and which is particle B.
Oh, they're twinning.
Now let's say they're twinning so much that they've separated distance from each other. And so let's say you have your friend, and you automatically think in your head, oh, person A is with person A and person B, right? But they might not even be next to each other. They could be like miles and miles and miles and billions and billions and billions of kilometers away from each other. Billions, but they're so entangled with each other that no matter when you observe them, it's like, okay, how are you this if this is over here, sort of deal.
Okay.
It is really confusing.
I'm not gonna lie. That was an obligatory but I'm like really.
No, this one I hardly understand because I don't understand the math behind it or anything like that. But essentially, like I was saying, so you observe two people holding hands, right? And then you're like, okay, that's a couple. They're coupled. And when they leave each other, not like leave the relationship, but they leave each other physically, they're still a couple. And so if somebody says, oh, I'm hanging out with like this person, sometimes if they hang out with each other so much so often, you can just assume the other person's there, right?
Okay, that makes sense. Okay,
you can just assume the other person's there, but they might not be there. They might not be there. So it's crazy because there are these particles that we can observe them, and it's like, oh yeah, these guys are together. They're holding hands. But in reality, one particle's on the other side of the universe and one particle's on the other side of the universe. So they're like super far from each other, and yet somehow they're still holding hands.
To see, like, that's so confusing to me, right? Because I'm just wondering, like if they're not in physical distance to each other, how do they link, right? Because it says they become linked, then they become indistinguishable. Is it like they have to be linked first and then they kind of become indistinguishable and then they become separated?
That's the crazy thing.
They don't have to be,
regardless of the distance. It's
just like a red string of fate, right? It's just like that red string of fate that goes across.
Exactly. Mind blown. Okay.
Yeah, I'm confused. The couple thing did not help.
I'm sorry. I try to use a real world example.
It's okay. Yeah.
I try my best. Because like it is just so
confusing.
mind-boggling. Yeah. Okay, I have a better example. So let's say you have a dollar bill, right?
Yeah.
And let's say that dollar bill is backed by a bar of gold.
Okay.
Right?
What do you mean backed by a bar of gold?
A dollar has value because its value is comparable in gold.
Got it. Okay, understood. Okay.
Right. Yeah. So if you have a dollar, that dollar is worth the same amount of a dollar of gold. So like if you hold both at the same time, it's like, I have a dollar.
Equivalent value.
Exactly. I have a dollar no matter which one I'm holding. If I'm holding the dollar worth of gold, I'm holding a dollar worth of gold. If I'm holding the dollar bill, I'm holding a dollar bill. But let's say that dollar bill that dollar bill you're holding is equivalent to a piece of gold that is on the other side of the world. And you can't see that piece of gold, but essentially you're holding the piece of gold because you're holding the dollar bill. So yeah, it is crazy. It's crazy. Somebody in chat said if one quantum event generates two particles, when you measure one, it instantly determines the properties of the other. So not at the speed of light, but instantly. So like it's like so if someone steals the gold, and the dollar bill disappears from your wallet, basically.
Okay.
So it's like because the dollar bill is backed by that gold, so that gold disappears. You no longer have that dollar bill.
Oh, what the hell?
So it's like crazy. It's just ridiculous.
It's very confusing, I will say.
Yeah.
It is insanely confusing. Okay.
Yeah. So it's really confusing, but I think that the dollar and the gold kind of made it a little bit easier to understand.
That made it a little bit understand. I think the part that made it easier to understand the most was how you said that if the gold disappears, so does the dollar. Okay, so exactly. Right.
Yeah, but it's linked only in that way that it's like once it's observed. So like if you observe the dollar bill, actually, I mean, I guess it works both ways. It's like, okay, so if the dollar bill is missing, then in your mind that the gold is basically missing as well because you no longer have the gold.
Got it. Okay.
Yeah, but if the gold goes missing and you have the dollar bill, basically it's like you don't have the dollar bill because the gold is missing. Yeah. So it's like if you've observed one, even if regardless of the distance that they are apart, like once it's observed, you can tell the exact properties of the other one. Oh God!
This one has caused the most pain on my brain. These last two sentences. Everything else I kind of get. Everything else I was like kind of understanding up until this point. I'm just like, oh my God, what the hell?
Yeah.
Okay.
She said Schrodinger's cat, but I honestly don't even think. Like, I think Schrodinger's cat makes sense, but I don't think it's in the same.
What is Schrodinger's cat?
Okay,
I've heard
so
the term.
Schrodinger's cat is this. It's basically, I guess it is basically the quantum entanglement. So basically, you have a cat. You put the cat in a box, and you've observed putting that cat in the box that the cat is alive. That cat is well.
Yeah.
Now you have a food bowl, and you fill that food bowl with food that is poisoned, and you put that food bowl with the poisoned food into the bowl, and then you put that poisoned food in the box with the cat. Now, when you close that box, and you walk away, you can walk away for 5 hours, 10 hours, something like that. The last time you saw the cat was alive.
So in my mind, it's still alive because that's what I observed.
So in your mind, it's still alive. But there's a chance that cat is also dead. And you will never know whether that cat is dead or alive until you open the box and observe it. So it can be both things at the same time. And a good example of this is looking at whoever
Schrodinger is a menace.
Yeah, right.
Why do you treat his cat like that?
Basically, it's just like a metaphorical thing, right? Because it's the same thing as a photon, right? Because a photon, if we observe it one way, it's a particle. If we observe it another way, it's a wave. Yeah. Like I mentioned that earlier. So that's like the whole idea behind Schrodinger's cat, because it has both qualities, but only if you observe it in one way.
Got it. Okay.
Right. So like the cat in the box is both dead and alive, but it's only one way if you observe it in that way.
I understand.
You have to physically see it. Yeah.
I understand. I think I
physically
understand.
see the cat.
So in the case of quantum entanglement, that would mean like the particles that are linked together, you only know their properties when you can observe them.
Exactly.
Otherwise,
oh my god.
So as far as you like, if you observe it once and then you leave it, even if it changes properties, you'll never know unless you observe it again.
Yeah, well, but it's more so like it's like two particles together, right? So like think of it like the two particles are the poison cat food and the cat, right?
Yeah.
Like they're together, but you only know if one is right, like the cat's alive or the cat's dead if you observe the one version of it. So if you observe the cat alive, that means that food was not ate, and you know that it hasn't been ate because the cat's alive. And so you now have observed both particles, even if you don't see the food. You can just say, oh, the cat's alive, then the food hasn't been eaten.
And same thing for if you observe the bowl. If the bowl was empty, then you know the property of the cat in that case. Right?
Exactly.
Got it. Okay.
So like if you observe one thing. Yeah, and the complicated thing about it is just when it gets to distance, right? Because like the distancing makes it really confusing, because even if those particles are light years away, I mean like an infinite amount of space away from each other, you can still predict what the other one is, even if you only observe the one particle.
Yeah, and that's because of the link, right? Like the link in the properties between them, like one will determine the other, essentially. In this case, like that's what quantum entanglement is. Okay,
exactly.
Okay, I am starting to understand it just a little bit more.
We understand it. It's just confusing.
It is insanely confusing. It is insanely confusing.
Yeah.
It's the idea of something being linked. It's the idea of something being linked, yet linked regardless of distance, and also the idea of how even if they are an infinite amount of distance apart, the effect, like what you do to affect the property of one will affect the other, even if they're, yeah. Okay.
Crazy. That's just crazy.
It's quantum entanglement. I don't like.
No, I don't either. It's just confusing. By the way, if you guys want to look at stuff about quantum magnetic levitation, I have this link here. Feel free to go check it out. This is an article that I referenced basically throughout this entire thing for anything quantum. Yeah,
can we get a round of applause for Jin for making this whole PowerPoint? Yay! I didn't even know. Okay, when I proposed the idea to Jin, I was like, we should just like read an article online. And I sent him a bunch of articles, and he was like, and he replied like instantly. He was like, oh, don't worry, I'm making a PowerPoint. I was like, you're making one? You're making a whole thing?
Yeah.
Holy shit, that's crazy.
Because I feel like if we just like watch something that somebody else has done, or like make something that somebody else has done, I feel like you don't get the same experience, right? You don't. It's not like
that's fair.
Because I can make it fun, right? I can make it fun. I can mess around with it. I can call electrons hoes and friends and stuff like that. Like,
and you can do the Xander. That's correct page. Can you go back to that real quick? Just for a second.
That's right.
Yeah, that's right, Xander.
Super hard.
I love this. They conduct super hard.
They conduct super hard. What is the superconductor?
They conduct super hard.
They conduct super hard.
Is that what you thought I was gonna say? Is that what you thought I was gonna say?
But basically what you said was that you just explained it. There's no other way to say it, right?
God. I feel like I should have put the joke. I feel like I should have run with it and just be like, what's superconductor? I mean, they just conduct really like hard.
Like no matter how you explained it, unless you were like completely wrong, this page was completely off. So I put it there. And because we had explained all this stuff leading into it, there was almost, unless you genuinely didn't understand anything.
You had a lot of faith in me, Jirakane. You had a lot of faith in my little peanut brain.
You're an intellectual individual. You know, you've got some wits up there. You're quick on your feet. So You've been RPing for the last 5 days. You can't say you're not quick on your feet.
Yeah, guys, this is me, Officer Tiny Wang. I'm back.
That's you have to make that
you
up
have
on
to
the
join
spot.
season 2, by the way. Oh god, it's so fun.
Yeah.
Anyways.
Oh gosh.
Oh my
gosh.
god. Well, thank you. I'm glad you think I'm smart.
Of course, I think you're very intelligent. You're very smart. Yes.
Thank you.
Of course.
Oh, you're also very smart because you did this whole thing. So I keep cutting. Go ahead. Yes, that is our.
That is our presentation on quantum levitation, quantum magnetic levitation.
All right. Now here comes the test, right?
Oh yeah. The test is at the end. So Remember we talked about all that stuff? Now we have to talk about all of these fun equations.
Oh my!
This is actually
we're actually going to
math
this?
behind it. No. I'm not gonna go into depth.
Okay, okay.
I'm not even kidding. Genuinely, these are the equations that are used within the mathematics sense of quantum magnetic levitation. Because we've got stuff like finding the magnetic field and
that's what the
finding
H is, right?
Yeah.
Okay.
Oh my god. So yeah, we won't go into this because I just don't want to look at math
cos
stuff.
omega. BA is that what that is? BA to the power of cos, like
Cosine.
cosine omega.
It's theta.
Sakatoa,
That's not omega.
Sakatoa. I that's why I know cosine from.
Cosine is part of math. But that's theta. Theta is just like a placeholder for a degree
Oh, okay.
of something. A degree of something. Yeah.
What's one on the left to that equation?
Oh god, what is it called?
The only thing I recognize here is pi.
Yeah, that's a.
And then
What was
E
it
is like
called?
E is also just like a placeholder for like any random integer, or in this case would it be integers only, or would it be like other things?
It's like it can be decimals and stuff, but usually you
Decimals,
want to
okay.
measure it to the what do they call scientific measurement? A specific scientific measurement. Excuse me.
Which is what is that? What is scientific measurements?
So
Is it like to a
so,
certain
for
decimal
example,
point, or
It is like to a certain decimal point.
like the sixth, the seventh decimal point, the eighth?
Yeah, basically like you only want to measure to like a certain degree, otherwise, because at a certain
could be
point it's like
inaccuracies.
an infinitely small. Yeah, there's inaccuracies. You want to make sure it's like good, and accurate, because otherwise, because if it's like 0.003. Is it 0.0039 or is it 0.0031?
One, yeah.
At a certain point, when it's so small, we don't care.
Yeah.
We don't care unless it like it impacts the equation. But at that point, it's so small it doesn't matter because it's not affecting the numbers in front of it.
Yeah,
so we
yeah,
just
yeah.
ignore it.
Okay.
Yeah.
Gotcha.
Math, ill. Theta
Yeah,
means
math.
tit
God.
Theta means tit in Spanish, apparently.
Wait, what? Fena means tit.
Theta.
Teta? Wait, where's teta?
Just in chat. I don't know. I think this is
Oh, theta.
No, not theta.
No.
But
You said theta,
yeah,
and then it became teta.
Yeah, exactly. Theta.
Okay.
Theta, yeah.
Oh, okay. Wow.
Hey, himbo, no, trust me. You can be an intellectual himbo.
Yeah, I mean,
You can. Have you seen the shit I do? Have you seen the shit
that's
I
true.
do?
That's true.
You absolutely can.
Yeah, you got. I just like you remember, guys. Remember to rewind back to the beginning of the stream where he introduced himself as, "I'm Jidakane, your himbo pirate," and then he starts talking about electric magnetic fields and quantum magnetic levitation.
That is
Oh
true.
my
That is true. I got my glasses on.
Oh my god.
Well, actually, today we're being intellectuals for once. I know, pretty different from your average VTuber stream.
Yeah. Oh my gosh.
Wow.
Oh. Okay, going back to all the way at the end here. I have these funny topics. Topics, right?
Yeah.
Hold on. I need to make sure I'm right on this.
Okay.
What is it called? Which one is it?
Magnetic leviosa. Quantum magnetic leviosa. Ronald Weasley. It's leviosa. Ronald Weasley.
Okay,
Stop it, Ron.
Okay.
Yeah.
Actually, this is crazy because this is a video that I literally watched in high school. But
Okay.
which one of these three topics is used on a smartphone?
Which one of these three topics are used on a smartphone?
This is literally on every single smartphone. One of these three topics is used.
Oh god. Tunneling.
Yes, actually, yes. It's actually insane. It's
you touching your touchscreen, right? And then it's actually affecting something on the that makes sense.
But it's like actual quantum tunneling. It's very interesting. It's very interesting because even though you're not necessarily touching it, you're you're transmitting electrons.
Yeah, you're
through a
transmitting,
pane of
like,
glass.
yeah.
Like, it's so interesting. Quantum Leap, an old sci-fi TV show. It is. I think it's actually Quantum. Yeah, it is Quantum Leap, I think. But Quantum Leap is actually an actual scientific term. So, but yeah, isn't that crazy? Quantum tunneling. It's used in real world applications. Your phone.
Yeah, my phone.
I mean, impossible. And I mean, it's measurable because it works, right? It's not like it's like.
Well, I mean, I'm like thinking about it. I'm like, I guess it kind of makes sense because like when you're, you know, doing something for an input on your phone, you're not actually touching anything, right?
Yeah.
But it's still
like,
still affecting stuff on there. It's registering your input, and it's.
Here. If we want, I can pull up the video.
All right, video.
Video.
Ending it off on a video is nice.
Yep. Okay, so let me go ahead and unmute this, and I'll make sure that I got the audio coming through on my end, so that way I can hear it.
Yeah. Make sure to turn off your BGM.
Oh, I don't have BGM going.
Okay. Silently
I've been a lot of
let me turn it down a little.
interest.
I've been raw dogging it.
A wonderful new type of touchpad technology that is going to be introduced into phones and touchscreens and various other types of household products.
This video came out 14 years ago.
This is something called quantum tunneling, or based around a material called a quantum tunneling composite. To explain it, we obviously have to get back into the wacky world of quantum mechanics and try and understand what the hell quantum tunneling is.
Wow.
What actually is quantum tunneling? It's another one of these bizarre quantum mechanical effects that arise because although we've got this picture in our heads of small particles, electrons, protons, even atoms, being like this, being like little footballs, in fact, they're not. They have a wave-like characteristic as well, and instead of being found definitively in this position, the particle can be found here.
Remember, we said it's both a wave and a particle.
It's both a wave and a particle. Yeah.
Region of space. It's not. It doesn't have a fixed location in space. If we've got a football, if we've got it in classical world, and it's coming along and it comes across to a barrier, it bounces off that barrier. Unless it's got an incredible amount of energy that it actually passes straight through, bulldozes through the door. Remarkably, with quantum mechanics, because you've got the probability of finding the particle here, and importantly, the other side of this door, there's because you've got a probability of finding the other side of the door, it means that the particle can actually go right through the door. Even more bizarre, there's a probability that the particle will be inside the door, inside the barrier.
If you and I were playing hide and seek, there would be a probability that you were hiding in this room, and there would be a probability that you were hiding out there in the corridor.
Yes.
But to get to the corridor, you would have had to get through the door.
Yes. Yeah.
Did the particle have to...
No, the quantum mechanically, the particle can literally pass through the door. It doesn't have to open the door.
Danny
it can
Phantom,
get through.
you know?
This appears mad. This idea of particles actually passing through solid objects, and it seems like quite an esoteric, weird phenomenon. Turns out that quantum tunneling pops up absolutely everywhere. The reason the sun shines, the fundamental reason the sun shines, is because ultimately particles, protons, tunnel through a barrier. In this case, it's an energy barrier. So what you have are two particles, two positively charged plates that come together.
They're talking about specifically just on the sun.
That repulsion for those protons is very, very large. But because they're not really little balls, because they have
the UV lays burning us is the ozone layer, though. You're correct.
Different positions.
You're right.
There is actually a probability.
We talk about the visible light. I guess technically it is both visible light and
my computer
and invisible light
and UV rays.
Since about 2005, there's been the development of what are called tunneling magnetoresistance hard disks, and these are based fundamentally on the tunneling of electrons through a barrier. Another example is a flash memory. In fact, the way these work, these random access memory devices, is that you store charge, store electronic charge on a computer chip, of course. And the way you actually clear that is that the electrons tunnel through a barrier. So coming back to this technology, this wonderful new touch phone, new touchpad, touch screen technology, how does it work? Well, what we have are nanoparticles, small chunks of matter, which are range between 2 up to 50 nanometers, so those size limits aren't particularly well defined. And the key thing that's happening here is that you're taking those nanoparticles, you're moving them together or moving them apart, and you're changing the rate of tunneling between those two nanoparticles. So let's start off. So the nanoparticles in the film look like this. They're separated by quite a large distance. There's very little probability, if any, for an electron to actually move from particle to particle to particle. So I come in with my thumb, imagine on this scale a very massive thumb comes in, squeezes the polymer, and what happens is that you actually move those particles together, and you're changing the rate of tunneling between those two nanoparticles.
Does it get really close?
What do I mean by that? You're changing the rate at which electrons can move across this gap between the particles. Now this might seem a little strange because when you look at that,
barrier
first
and
of
a
all,
gap,
it
it's just
seems that, well,
barriers.
there's no barrier there.
Yeah.
In fact, for the electrons, there is a barrier. There's a very strong barrier because you've got a gap. You have got vacuum. It's just like if you took.
So you're closing the distance and making it so it's a lot easier for them to.
The wire
pass
in the
through.
circuit, and you're left with a gap. Electrons won't flow. Classically, electrons won't flow across that gap. But if you make that gap really, 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 really small, down to the nanometer level, then you will actually see electrons flow. When you change the gap between these particles a little bit, it's not like you get a small change in the tunneling probability. You get a huge change in the ability. It turns out that for every angstrom, for every 1/10 of a nanometer, in many cases, you will get a change in the probability of an order of magnitude, of a factor of 10. So for every 1/10 of a nanometer you move these particles apart, you're typically talking about a factor of 10 change in the current between particles. So what we have here is when we bring them together, we see this rapid rise in the tunneling probability. We see this rapid rise in the ability of this film to pass an electric current. And so simply by applying pressure to one of these polymer films, these polymer nanoparticle hybrids, you can change it from an insulator to a metal. And in fact, you can go from a resistance of 10 to the 12, a million ohms, to 1 ohm by applying pressure.
So by applying, so by applying pressure, it's similar to, remember how if we cooled it down, it has zero resistance. Super cool. It's zero resistance. This is basically the same thing because you're applying the pressure and it's making the space tighter. So,
okay.
So it's getting rid of the resistance, and by doing that, you're allowing the electron to slip through.
Gotcha.
For an electronic device to pick up that change in resistance. And from that, the key thing is that they are arguing, and quite correctly arguing, that they've moved from a 2-dimensional touchscreen to a 3-dimensional touchscreen because you've now got
Isn't that crazy?
force in that direction. I guess what really fascinates me, and there are other part of 60 symbols where I've waffled on about this at length, but what really fascinates me, we've got this incredibly esoteric and incredibly difficult to grasp concept or concepts related to quantum mechanics, and yet time and time again, despite the fact that there are huge philosophical gaps in our understanding, we still can apply it. And the quantum theory, time and time again, when you apply it to the real world, does a remarkably good job of explaining how nature works.
There you go. Quantum tunneling in smartphones.
Holy shit.
Holy
Wait,
shit.
what was that measure? What was the unit of measurement he used? He was like a 1/10 of a nanometer.
Yeah.
Or onk, he said?
What?
He said he used a name for a 1/10 of a nanometer, and it was like an ank or an onk or something.
Oh yeah, angstrom.
Angstrom. Oh my god. Yeah. You guys, there's measures.
It's crazy with it.
Can we go through like measurements of a distance?
Is a unit of length equals to 10
to the power of negative 10 meters.
Yep.
Oh
or
my
0.1
god.
nanometer. So an angstrom is a very, very small unit of measurement.
Okay, wait, what is okay?
Small.
Wait, can I get you to go up from angstrom all the way to like
oh god.
Meter?
Metric. Hold on. Yeah. Oh, what would it be called? Units of measurement.
Metric, right? This is metric, not imperial.
Yeah, metric. But I'm trying to think what it would be.
I don't know, if you just type angstrom in there, it'll probably like give you a list of all of them starting from angstrom.
True, maybe. Wikipedia.
Oh, flashbang. Who is that?
Flashbang.
Handsome man.
This
Anyways.
is Anders Engstrom, the guy who...
Oh, the person that discovered the angstrom.
Yeah. Pixie's on top of it. Okay, so angstrom, atto, femto, pico, nano, micro, milli.
Nano, micro, milli. And then
Yeah,
meter.
so yeah, and then no,
What
not
about
meter.
centi?
It's milli, centi, meter, kilometer.
Kilo. Oh,
Kilometer.
Okay, kilometer. Okay.
Yeah.
And then
But
there's
the reason
anything
why
after.
we don't see. Well, this is why we see like kilometer instead of kilometer is because kilos is like a unit of
A
weight.
unit of weight measurement. Okay.
Yeah.
And then what?
So-
Is there anything after kilometers? Probably not, right?
Technically yes. What is after a kilometer? I don't think we measure like say greater than that,
megameter
but it
metric
does.
system. Is that what it's
Yeah.
called? Okay.
Yeah. So megameter, gigameter, terameter.
Gigameter, megameter,
Gigameter.
gigameter. This sounds so chuny. This sounds so chuny. This sounds so chuny.
Yeah.
What the?
So it goes to
Decameter.
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 Oh, megameter. No. But yeah, it's just because it's easier to say that than to say, oh, I have 1 billion meters. You can say I have 1 gigameter. Or say
You better
like-
watch
like-
out. I'm gonna use my
what is past
smash,
billion?
and it's gonna hit you with a gigameter of.
Yeah, exactly. So like instead of saying like I have 1 trillion meters, you can say I have a terameter.
Wait.
It seemed like
yeah,
with
what is-
units of like
Yeah.
What is-
No, I was gonna say what's after 1 trillion. What's after trillions?
I want to say quadrillions because it goes by like
Quadrillions?
number.
Yeah, quadrillions, and then heck.
and
wait,
then
no.
pentamillions.
Pentamillion and hexmillion.
Let me see.
Octomillion.
What is after quadrillion? I think it's. Okay. Whoa.
Trillion, quadrillion, quintillion, sextillion,
sextillion,
septillion, right? Septillion for 7.
septillion, octillion, nonillion, nonillion,
Nonillion,
decillion.
decillion.
Yeah. It goes decillion and then undecillion,
But, unlike 1. Okay.
I guess. And then unlike 1, and then duodecillion, and then tridecillion, and then
Dude, holy shit. Okay. So it kind of
quatordillion,
like
quatordillion,
like quattro, like 4, and then so
Yeah,
it's like 4 plus like I guess like the naming is 410 million.
Holy crap.
Quattrodecillion. But that is crazy.
Yeah, it goes, but like obviously we never see numbers like that, right? You know what? I had a realization the other day. Because you always hear people like, oh, in my mind, like $1 million is like a lot of money, and somebody being like a multi-millionaire is a lot of money. And then I sat down and I thought about it. So if somebody's a billionaire in this world, that means that they've exceeded the amount of $999 million.
Yep.
And if you look at that on a numerical size, like that's a lot of money.
That's a lot of money. It's a lot.
Think about it. If I think of $100 million, right?
Yeah.
$100 million. That's like a massive amount of money. But if you think of it about it, you need 10 times of that to get to $1 billion.
I remember reading an
That's
article
a
about.
lot of money.
I remember reading an article about like how like millionaires, like the disparity between like a millionaire and a working class.
Yeah.
And then apparently the disparity between a millionaire and a billionaire is like thousands of times the disparity of a millionaire and a working class.
Yeah, hold on. Let me see. So, okay, so.
Wait, actually, there's a video. I want to check out if you want to check it out.
Okay, yeah.
Have you ever casually explained?
I don't think so.
Okay, if you go on YouTube, you look up casually explained.
Yeah,
and then he has a video called Levels of Wealth or something. Something wealth.
Casually explained Levels of Wealth.
It's,
All right, let's watch it.
When we think of money, it's usually in
I
terms
love this
of
guy.
what
He's so
things we
funny.
can buy with it. But your level of wealth doesn't only determine what you own, it can determine entirely what your life looks like. And I wanted to give a bit of an overview of what that could look like at some different intervals.
Okay.
Now, at the bottom of the pyramid, of course, we have the alcoholic and abusing life who move off public services because they can't pay their debts. Fucking grad students.
Fucking grad
Disgusting.
Oh my,
The working and middle class.
that's
makes up about
crazy.
90% of
Wait, it
population.
says grad
That might
student.
seem
I
like they
love
can't
the
accomplish
way
much
this guy does his
compared to the
videos
elites
is
of
so
society.
funny.
Usually the
It's
middle
so
class work
funny.
together to become much more powerful. As an example, with one roommate they can afford rent, but with two they can afford furniture. The middle class earns up to $300,000 a year, but the median individual income is a lot more.
Whoa, the middle class goes
Yep.
to 300,000?
Yep. That's still considered middle class.
Whoa.
Yeah.
Whoa.
Yeah.
10,000? No, there's no way it's a 10,000 is middle class. There's no way.
No, well, I mean,
That's
like the media or like the large amounts of them are around 38,000. But this was 6 years ago.
Yeah, but 10,000 being middle class sounds like it's ridiculous. That's
I think that's in
you're in poverty at 10K.
that's in perspective of as like a single
Like
person home though.
Yeah. Okay. I'm sorry. If you're a single person home and you're able to live off of 10K, that is you must not need to pay for gas, you must not need to pay for rent, taxes don't exist, you're not feeding yourself, like that's insane, that's crazy. Oh my god.
Yeah,
I can see 10K being a livable wage if you're like smooshing off of like your parents and
That's
like
true.
living with
That's
your
fair.
parents
That's
or
fair.
living,
Yeah.
or living with somebody else who's taking care of like all the other expenses. But is this for the whole world of the US? Considering it's in US dollars, I would have assume it's in US.
I don't know. He doesn't really cite it in the video.
Yeah. I want to say this guy's from the US, so it's probably related to the US. Rent
Yeah,
control.
that makes sense.
Food stamps. No, actually, like, how do you live off of 10K?
How would you?
That's
Yeah,
insane.
I'm just trying to think. Like, what is the mean? Hold on. Don't click off the video. I'm gonna Google this real quick. Okay. Lowest hourly wage America.
Lowest hourly wage. Okay, minimum wage. I think the lowest I've ever seen is $7.
Okay, yeah, $7. Okay,
I'm pretty sure that's the minimum of minimum wage.
Apparently, in Wyoming and Georgia, it is $5.15.
Okay, that has to be like $5.15 if you're like making tips or something like that. There's no way.
That would make sense. That would make sense.
Yeah, there's no way you can humanly possibly work for $5. At least in the US. Guys, remember, Jeremy, you just said that it's far lower in Southeast Asia, but you gotta realize the cost of living in Southeast Asia, unless you're like in Singapore or like some super wealthy city, is exponentially less as well. So it's like, yeah.
Okay. So I think I'm starting to
money is different, but yeah.
I do want to say I'm trying to understand where he get the statistic from, because if we look at the $5.15 hourly wage, it comes out to an annual to about $9K. An annual about $19, right? But that would probably be reported data, not including tips. If that would make sense, right? It'd be like restaurant. So that's probably what it is. That's probably why, like,
I can see.
So maybe like that 10K, that big curve at 10K is probably including a lot of restaurant workers, waitresses, waiters, bartenders, things like that.
Do you see my mouse on the screen? I hope.
I do see it.
Wait, the goal is to be like around here.
Right? Yeah, around there.
If you're over here, it's nice, but I feel like taxes start getting a lot more expensive and stuff. If you're like right around here, this is the chill zone.
Depends on the tax bracket of it depends on like how your country does their tax brackets though. Because apparently,
I guess if we're talking U.S. Oh wait, you're Canada too.
Yeah, I'm Canadian.
Oh my god, right? I forgot. Yeah, Canada taxes are crazy.
Canada taxes are freaking crazy,
I
dude.
forgot about that.
I think it's like I think on like every paycheck, it's about like 20% is income taxed. Like 20% of income is taxed to the government.
Oh my gosh, yeah, right.
It's terrible.
Okay. Ida, to inform you of the switch in topic. So essentially, we started talking about units of measurement.
Yeah.
Yeah, so we were talking about physics, and then we were talking about Xander was asking what like an Armstrong.
Yeah, what's that? What's an
angstrom?
Yes.
And an angstrom is basically a unit of measurement that is so small. It's like it's like whatever. It's like 0.1 nanometer. An angstrom is 0.1 nanometer. And then we were like, okay, so what are the user measurements? And I talked about how exponentially large $1 billion was compared to like the millions, right? Because let's say somebody has $100 million. Oh my god, that's so much money. Wow, that's so much money. Yeah, now multiply that by fucking 10 and
10
that
times.
is
10 times.
That is $1 billion. That's so much. That's
right?
so much. Like think about it this way. You make 100K, you need 1,000 times to get to. Okay, so if it's 100K
if
times 10 is 1 million.
Yeah, that's 1 million.
Yeah. Oh my god. Quantum economics. Yeah, how interest rates have entangled with inflation. That is awesome. Oh my god. All right, but yeah, I feel like this is the comfort zone. At least like if you're here and up, you're chilling.
I mean, there was a study
and below.
Yeah,
you're also chilling, but like you're cutting things to like
you start to think about how you're spending. Like when you're up there, like you kind of don't have to think about how you're spending. But there was a study done where the difference between someone who makes it was like this: the difference between someone who makes 5K annually and 50K annually was huge in terms of like happiness and comfort and everything else. But the difference between someone who makes 50K and 500K was abysmal. Like a very small difference in terms of happiness and everything, which is crazy to me. It just reflects.
Here's the thing.
Yeah,
it's sort of like it's like clothes, right? So let's say you make $50,000 a year, right?
Yeah.
The clothes you get are going to reflect that price range because you're not going to want to spend or have the need to spend more than that.
Yeah.
But at the end of the day, clothes are all about functionality. So whether you're wearing a pair of clothes, whether you're wearing a pair of shoes that are worth $500 or a pair of shoes that are worth $50, the functionality is the same. And generally you're getting the same happiness off of it.
Yeah.
Right. Once you're at this like crazy like 300,000, 500,000 range, like the happiness you get from purchasing something is gonna be about the same as the happiness you get from purchasing something down in like the 50K range.
Yeah, exactly.
Yeah.
I think a lot of it comes also from like what's it called? My brain. Hold on. A lot of it comes from learning to be content, right?
Yes. Absolutely.
The how you learn to be content in relation to, it's usually in relation to the income you make and lifestyle you can afford. And if you're making like a lot of money, but you can't feel content with the way you're spending it, then that's also like a big factor in your happiness, right?
Yeah.
So True. All right. Video
continuing. Yeah.
This can be pretty misleading though, because if you're 50 with a wife and 2 kids, 38K a year is pretty rough. True. If you're 21 and single, you're buying resale Yeezys thinking, I wonder how much sex I'd have. So in conjunction, I think there are a couple lifestyle indicators to check to see if you're in the
That's what I'm saying. Like,
that's
what I was saying earlier.
Had 5 kids, your parents had 3 kids, and you're gonna put a stop to it once and for all. And you don't have an emergency fund because you figure that if you're on vacation, your appendix gives out. Why would you spend 20K on surgery when you could just die? So even beyond the middle class, we get to the start of your truly wealthy people. These are the notorious 1% who typically have an individual income of $300,000 or higher, or a net worth of over $8 million. Usually this means you have more than one home, active investments, travel whenever you want, and basically have the best of everything short of private jets and a Battlefront 2 season pass. But in the same way someone in the arts might wave their fist at an accomplished engineer, there's a huge difference between people within the 1%. As an example, if you're worth $75 million, you have the ability to see almost anyone in the world just by asking. But if you're worth $75 billion, you have the ability to see almost anyone in the world without asking. That's
true.
That's why they use Mark Zuckerberg.
And if you're not famous, you at least have a Wikipedia page that you didn't make yourself. You likely make up to $10 million a year, which to compare with the more normal income,
not the Black American Express
card. I know.
Hot dog, getting 100 hot dogs. I don't know why I left that in. At this point, your wealth is almost magnetic to more wealth, and ironically, things start costing less. I could pay $5,000 for a Gucci suit, and people might think I'm cool, but if I were actually cool, Gucci would have paid me to wear it. While it sounds pretty great,
that's so true.
That's so true.
Yeah, exactly. Or only like you because you're rich and famous. Fortunately, though, you are.
That's a good point he made.
Mm-hmm. So finally,
when you have that much money, money becomes magnetic to money.
Exactly. 0.001%.
Whoa.
Guys like Elon, Jeff, Branson, and Bill. These people have so much money they can literally change the world. Save the kids? Done. Create your own space program? Done. Dinner with the president? You are the president. You don't fly business, you buy business. When you get pet supplies from Amazon, you mean the rainforest. And when you say, hey babe, how about I drive this time? You're talking to the car. If you look at the absolute top, Jeff Bezos recently overtook Bill Gates, and to be as rich as the two of them, you would have to earn about $5,000 every minute you were alive.
Oh my god! Oh my god!
Okay, you know it's so crazy too. So there's this random little like mini game, or like itch.io or something, I think. Where there's like people put like a bunch of games. Someone developed like a text game called I Am Jeff Bezos, right?
Oh my god!
And then in that game,
I think I know what you're talking about.
Yeah, dude. In that game, okay. Right now, I think Jeff Bezos' net worth is currently $159 billion, something like that, right?
That's so much.
To put that into perspective, in that game, it's explained that there was a hurricane that hit like Puerto Rico, right? And like a lot of houses were devastated and everything. The amount it would cost, the amount of cost you would need to fix that entire like city or state or that town area would be 59 billion. I think I was like, yeah, and like,
wow,
and that's
you
like
could devastate an entire country and still have like
and have enough money to fix it. Have enough money to fix it.
That's insane. Oh my god.
I don't think I could even spend money if I tried.
Oh my god.
Fucking amateurs. Now, the pyramid capped off, if we step back, it does seem like the implication here is that your life gets better the more money you have, which brings about the age-old question of, does money buy you happiness? And from what I've looked at, I think the best explanation is that money won't buy you happiness, but it can make problems go away that make you unhappy. Like when you go to take money out of your bank account and get charged a fee because there's no money in your bank account. When you buy tickets online, you have to pay extra for doing all the work yourself. With that said, I wanted to end it at that point, but I showed my friend and she said, is that it? This first world country? What about the rest of the world? And
oh my god, Drew!
Like they say, you can't make your sneakers and wear them too. The good news is that my demographics show that there aren't many people in third world countries watching my videos.
Oh my god, so you literally was talking about the US. So,
I know, dude, I fucking love this guy. He's so funny. He's so funny. I love him, man.
The Castbox app or website.
Oh my god.
Oh my, can we
crazy.
Can we do like a stream where we just react to his videos, because his videos are so funny.
I'm totally down. I'm totally down.
Let's do it next week.
We can do that
Let's do it next week
for sure. No, actually. What the fuck?
Oh my god, his videos are so funny.
This reminds me of like the history of the world guy, the guy who like
knows
the world.
Yeah,
he's like,
dude, I love that video. It's so like wacky, and it just it hits my ADHD like so well. Like the history of the world video hits like his little like the music he uses, the colors, the freaking neo graphic colors is so
Comic
funny.
Sans with the neon.
Comic Sans. Oh my god.
Oh my god.
Oh,
that's so funny. Gosh. Alrighty.
All right.
Well, I think that is all the time we have for the stream. So I hope you all learned about quantum mechanics, economics, and units of measurement.
And apparently levels of wealth in the world.
Yeah. That's crazy. That's crazy. We've done it all today.
They don't have internet.
No. Unfortunately, I'm looking at third world countries. They don't have internet. That's crazy.
I was like, bro, it's so good though. It's crazy. So good. Oh my god.
Oh my god.
Zan, we loved it. My chat says they loved you, Jin, by the way.
Wow, thanks guys. Love you too.
Yeah.
yeah. And my chat said, Xander, you a bitch. Wow, that's kind of mean.
Makes sense, honestly. I mean,
no, actually, nobody said that. Nobody said that.
Okay, well, then you said that, so fuck you. Jin, you a bitch. No, just kidding.
You a bitch.
You a bitch. All right. Okay.
Alrighty. Yeah.
All right.
Yeah.
Guys, thank you so much for watching us. Oh, yeah. I'm going to go see us. But guys, thank you so much for watching us.
You're on YouTube right now?
I am on YouTube.
You're on. Okay, let's see if we can.
No, don't rate it to me. I'm literally ending stream. What do you...
No, I'm not rating it to you.
Oh, like we want to rate it to the same person?
Why would I want to rate it to you? No, I'm kidding.
Yeah, no, that's what I was gonna say. I was like, huh?
No. No. Yeah, let's see if we raid the same person. Let's see.
Let's see who's streaming. Bum 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 bum
Bum, 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 bum.
bum. Want to raid into Octavio?
I was actually just about to say that. You want to raid in Octavia?
Yeah, let's raid in
I was
Octavia.
just about to say that because he's the only. Yeah, I think that'd be good. Let's do that. I
Okay,
don't
let's
even know how to do it. Every time I try to raid on YouTube, it doesn't give me a raid notification.
Make sure that when you set your raid, like you know how to set the rating too, right?
I go to the customization and then I go to redirect.
Okay, and after you set your raid, make sure you're not ending your stream from OBS, but you're ending it from the YouTube analytic live stream controller. Yeah, that's the part that messes everybody up. So you have to go into YouTube Studio.
It didn't used to do that though.
It didn't. I don't know when they changed it, but they changed it, and it sucks.
Oh, weird. Okay, well, I'll do that. Good to know.
All right.
All right, ending screen.
All right. Oh yeah, let me go to the ending screen. Bye guys. Bye.
Bye guys.